Right. Good morning, everybody. Thank you for joining us for our webinar series. My name is Kendra Jolly, and I am the Partnership and Grants Coordinator here at the Invasive Species Center, and I'll be your moderator for today's webinar. So before we get started, I would like to acknowledge that the Invasive Species Center honors the long history of First Nations, Inuit, and Métis Nation peoples on the lands now known as Canada, and strives to show respect to their ancestors, their communities, and to them individually. We greatly appreciate the significance of the lands, waters, and all living things, and offer our gratitude to the Indigenous peoples for their care and teachings about our Earth. Our relationships with the Indigenous communities are important, and we will continue to listen and learn how we can be in a good relationship with Indigenous peoples, the lands, waters, and all living things accordingly. The Invasive Species Center respectfully acknowledges that our head office is located on the traditional lands of the Anishinaabe, the Batchewana, and the Garden River First Nations, as well as the longtime settlement of the Métis people in the Robinson-Huron Treaty area. The Invasive Species Center is a not-for-profit organization that connects stakeholders, knowledge, and technology to prevent the introduction and spread of invasive species that harm Canada's environment, economy, and society. We've got a lot of great invasive species resources on our website, including species profiles, best management practices, and more. So please check us out at invasivespeciescenter.ca. You can also sign up on our homepage for our newsletter, bi-weekly media scan, and event invitations, which is where you are able to hear about upcoming webinars in our series. The Invasive Species Center has also launched a new invasive species training program that offers virtual courses on topics related to invasive species. We currently have 2 courses available, which focus on different forest invasives, but we'll be adding new content regularly, so please stay tuned for that. Make sure to check out our website and sign up to receive updates on when these new courses may be available. Before we get started with today's webinar, there are a couple of things that I do want to mention. There will be time for questions at the end of the webinar. So if you do have any questions at any time, please enter them into the Q&A box in your down in your doc, and I will read those to our presenter after the webinar to ensure we got those questions answered. I'll also be putting the information for her email into the chat box. So if there's any other questions that we're not able to reach or to get to, you do have the opportunity to reach out to her directly. We have also enabled closed captioning. So if you'd like to follow along that way, you can turn that on through your taskbar. If you're having any difficulties at any time, please enter them into the chat box. We'll do our best to resolve them for you, or you are able to respond to the email that was sent out with the registration. And again, we'll try and resolve that for you. Lastly, there will be a very brief survey coming out after the webinar. So if you could take some time to fill it out, that would be extremely appreciated, and it does help us out. So today's webinar is titled Lower Temperature Thresholds of Lycorma delicatula, and I am pleased to introduce you to our speaker, Anna Turbelin. Anna is a postdoctoral research scientist at the Great Lakes Forestry Centre in Sault Ste. Marie. She has a PhD from King's College in London, UK, on interactions between invasive species and natural hazards. She's a postdoctoral researcher at the University of Paris-Saclay in France in the Ecology, Systemic, and Evolution Department, working on the Invasive project. And her research interests are in invasion science with current focus on the thermal tolerance of the spotted lanternfly, or Lycorma delicatula. And with that, I am going to hand over our webinar to Anna, who is going to take us through her speech this morning. Thank you.
Hi, good morning. Okay, so I hope you can all hear me fine. Thank you, Kendra, for the introduction. I will be presenting some work that I've been doing with Amanda Rowe on the cold tolerance of spotted lanternfly.
Sorry to interrupt you, Anna. We do see your notes and your next slide on the screen at the moment.
Sorry about that.
Oh, that's okay.
I'll go back to the screen sharing. Is that better?
There we go. Yep, now we just see your
Okay.
title slide.
Perfect, thank you. Okay, well, starting again. So first I'd like to thank our funding bodies, so the Canadian Food Inspection Agency and Surgeons International, but also our co-authors, Brent Sinclair and John Roast. Really, I'd like to thank Alice Liu, Aisling Wardrow, Kaylin Carcason, and Raya Ash for their support processing all the nymphs and running some of the experiments, and as well as Chris McQuarrie for some of his help on the analysis. I want to thank the Invasive Species Centre for hosting me today, but also for sharing, I don't know if you can see my cursor, but those lovely icons of spotted lanternfly. Finally, I want to say that some of the images are from iNaturalist, but also are AI generated. Hopefully you can tell the difference as the presentation goes through. And I want to thank Penn State Extension. They have shared some of their background slides with me, and you will see some of them in this presentation. So about the talk, I'm going to give you a bit of background on spotted lanternfly and go through our project on cold tolerance and also what the implications of our results are, as well as some of the risk to Canada. Spotted lanternfly is a really beautiful insect, at least from my point of view. It's Lycorma delicatula. It's a Hemiptera from the Fulgoridae family. En français, c'est le Fulgor tacheté. It's a planthopper native to China and Southeast Asia. It currently has invasive population in Japan, in South Korea, and in the US. It overwinters as egg masses, so it's that little blurb that you can see here. Those are laid in the late summer, fall, so September to November, and they hatch in April through to July. So here you have first instar nymph, second instar, third instar. They turn to fourth instar from July through to August, and adults emerge in late July. The egg masses, which is an important factor for experiments, actually, are covered in a waxy coating that you will see later. So first to third instar nymphs are quite distinguishable. They're black with little white dots. If you happen to go in an area that has spotted lanternfly populations, then you can look out for those at the moment. That's what they should look like right now. Fourth instars are similar, but they have red on them, so black-red with white dots. And then adults, which have made it on Saturday Night Live, are also quite remarkable. Yeah, they have a yellow and red on their abdomen, and their wings are spotted. Generally, the adults, like nymphs, can often be found on the tree trunk or at an union between the branches and the trunk. But you can also see them on whole trees. This is quite an important infestation. It's not uncommon to see a mix of the different life stages at once. So if you're out looking for them, you could find a mix of them feeding on plants. For hosts, spotted lanternfly has a wide range of hosts, and that includes important trees in Canada, like maple, walnut, willow. Its main host is the tree of heaven, another invasive in North America, is Elanthus altissima. Its nymph host range is really quite broad. It feeds on pretty much anything, including sunflowers, cucumber. But as it grows into adults, it really narrows down. It feeds on over 70 species of plants and threatens agricultural communities, including grapes, stone fruits, and hops. It is a phytosanitary concern in forestry, and its survival is not limited by tree of heaven. So tree of heaven doesn't have to be present for it to survive. The adults and nymphs, they suck sap from the stem and branches using the piercing mouth sucking parts. And they generate a lot of honeydew, and that waste product promotes a lot of mold growth on plants. Now, spotted lanternfly is not a tree killer. It has not been observed to kill plants except tree of heaven, some small saplings, and some grapevines. But it is a plant stressor, so it could add additional stress to plants that are already stressed by disease or climate conditions. In the US, it was first discovered in Pennsylvania in 2014, and despite continued controlled effort, it's continued to spread outside of quarantine zones, and now infestations are in 21 states. There were new infestations in Illinois, Iowa, and Tennessee. And for a Canadian point of view, there were populations detected in 2022 in Buffalo, New York, and Pontiac, Michigan, so really quite close to the border. Naturally, spotted lanternfly is quite a slow disperser, but it lay eggs masses on smooth surfaces on pretty much anything. You can see here tires, so it's not just trees, garden furniture, and it can spread long distances via human transportation, whether that's cars, lorries, trains, but also airplane and cruise ships. Currently, the spread for spotted lanternfly actually seems to follow some of the models. It's extending north and going west. And it's expected, one of the models expected to reach California by 2033. There have been some observation of it in California already, so who knows, it could be a lot sooner than we'd hope. Now, all these models really use the available data on temperature thresholds for spotted lanternfly. So those biological data are from South Korea, but we don't really know if the lower temperature limits in North America are comparable. As an example, one of the models by Young and al. Uses -11 as a cold threshold for spotted lanternfly. Which leads us to our project, assessing the cold tolerance of spotted lanternfly from populations in the US. And our Canadian perspective really was to try and answer if spotted lanternfly can survive winter in Canada. The models do show that it can survive in Canada, although we know that hatch rate is sensitive to natural winter temperatures. So again, our question is, what are the thermal limits of the North American populations? For the cold tolerance strategy, so we looked at the cold tolerance strategy, whether it died before freezing, when freezing, or if it died, or if freezing wouldn't kill it, so whether it's chill susceptible, freeze tolerant, or freeze avoidant. And we also looked at lower thermal limits. Our egg masses were acclimatized in the field in near Reading, Pennsylvania, I think Blue Marsh Lake. and they were collected on the 20th of December from the field by John, and placed in a cool chamber at 6 degrees until they were shipped to our insect production quarantine facilities here in Sault Ste. Marie on the 19th of January. So before we did our experiments on cold torrent strategy and thermal limits, we actually ran 2 experiments. We looked at whether manipulating eggs had an impact on the hatch. And so we took 10 egg masses. I want to say these are not the pictures for that experiment, so you do have to use your imagination. This is a picture of an egg mass. Actually, you can see that some have hatched, so that's an egg mass that has hatched, but it does look like this. We removed, carefully brushed off some of the wax covering for half of the egg mass and removed half of the eggs, and then we left half of the eggs intact. And then we placed them on Petri dishes until, well, they completed their chill requirement, and put them out to hatch to assess whether removing the eggs would have an impact on hatch. And actually we found that egg manipulation did negatively impact hatch rate. So if eggs were left intact, they were more likely to hatch than when removed from the egg mass. After that, we also measured the supercooling point of individual eggs. So we took 8 eggs from 5 different egg masses. We stuck thermocouples to them, placed them in tubes that went into a circulated refrigerated bath. We cooled them at a rate of 0.5 degrees per minute until they froze. So we identified a supercooling point from the freezing exotherm. So when the heat is released, when ice formation occurs, and this is what we found. So supercooling points for egg masses, well, individual eggs range from minus 17.4 to minus 27.7 degrees C. So this was done to be able to inform our experiments. So for cold torrent strategy, we roughly knew what temperatures to lower it at. Here we did a similar process then for the supercooling point, but we compared the hatch rate of groups of frozen and unfrozen eggs exposed to the same low temperature. We took 8 eggs from 4 egg masses, from 4 different egg masses. And once half of the eggs had frozen, we removed all the eggs from the cooling block. So half of them froze, half of them didn't. And then we assessed hatch rate. Well, first we returned them to 6 degrees to complete chill requirement, and then placed them in a personal chamber at 25 degrees to assess hatch. What we found is that they all failed to hatch at or near the supercooling point. So around minus 24.8 for these individual eggs, which makes them chill susceptible. Because they're chill susceptible, supercooling point is in theory not really that informative. And so to know really at what temperature they die, we assess the lower thermal limits. Based on previous experiment and also the study by Park 2015, we decided to do short-term and long-term long exposure experiments, so 1 hour, 12 hours, and then 10 days and 15 days at a range of temperature, so going from 0 degrees to minus 25. The egg masses, the experiments, we ran them from end of January until the end of February to coincide with the lowest winter temperatures. What we did is we placed individual egg masses into falcon tubes. So this is a picture from after, but you get the idea. These were sealed, placed in the circulating bath, cooling with the circulating bath. We lowered the temperature at 0.5 degrees per minute up to 0, and then after that at 0.1 degrees up to the treatment temperature, and they remained at that temperature for the duration of the treatment. Then we place them back at 6 degrees to complete diapause and set them up for emergence from the 31st of March, so in a Percival chamber at 25 degrees until hatch. Based on our preliminary work, so we did do 1-hour experiments over the previous year, and the results from PARC, this is what we expected to see. So we expected to see hatch in 12 out of 22 treatments. So here up to -20 for 1 hour, up to -15 for 12, up to -10 for 10 days, and -5 for 15 days. We didn't really know for -22 because in our first year, we did observe a hatch at -20 for an exposure of 1 hour. What we found was actually hatch in 18 out of our 22 treatments. And that included hatch at our lowest treatment in 1 hour, so -25 for 1 hour. Of those that hatched at -25, actually one of them nearly had 100% hatch in the one egg mass. And we also found, surprisingly, I'm not sure which one's the most surprising, we got hatch at -20 for 10 days. This is just another way of seeing the data. This is a box plot showing the percentage hatch per egg mass in each of our treatments, exposure treatments. So we are control. So egg masses that were not exposed to any treatment, the median hatch was 49% and the mean hatch was 44%. Actually, we found that the highest hatch rate for egg masses were those exposed to -10 for 10 days. This was higher, but not significantly different than for egg masses that were not exposed to any treatment. So hatch rates were significantly impacted at our short exposure from -20 onwards, and for the long exposure treatments from -50 onwards. Overall, we found that spotted lanternfly from Pennsylvania can tolerate temperatures at least 5 degrees colder than predicted for South Korean population. Now, we know that eggs survive temperatures near the supercooling point, so we have -25, but because we had the hatch at -25, we don't actually know how low they can go. So we suggest that the lowest supercooling point that we observed, -27.7, is an approximation of the LT100, so the temperature at which 100% of species of individuals would die. Now, I really want to stress that this is an approximation because some insects can increase their cold tolerance in response to local climatic conditions. The example here is the emerald ash borer, and northern climatic condition has actually depressed the mean supercooling point for this insect by at least 12 degrees relative to southern population. I think, if I remember well, that's depressed it to something like -52, which is crazy degrees C. Now, those differences can be linked to a range of factors, and that includes methodological differences in the experiments. I'm talking differences between population in South Korea and North America, so experiments that have looked at cold tolerance for egg masses. It could be phenotypic plasticity and also genetic adaptation, or a combination of it all. For the methods, the difference here is that Park removed individual eggs from the egg masses, and we did find that egg manipulation negatively impacted hatch rate. So maybe those differences are actually linked to an effect of manipulation rather than treatment temperature. It could be phenotypic plasticity, it's possible. That's when individuals would respond to environmental cues. And in this case, they would increase their cold tolerance in response to the local climate conditions. It has been observed in other insects, like I mentioned the emerald ash borer, but also in spongy moth. So it's possible that spotted lanternfly responds to environmental cues. Actually, we did, so I mentioned we did preliminary experiments, and those were in the fall of 2021, but that's when they were, let me start again. In the fall of 2021, they were exposed to different temperature than in the fall 2022, and October of those 2 years was actually significantly lower than October 22 was colder than October 21 to make it more easier. And we did observe hatch at -25 for our egg masses that were collected in 2022, but not in 2021. So who knows, maybe there will be a greater cold tolerance capacity that could be observed based on autumn conditions that are experienced by spotted lanternfly. Could it be adaptation? Maybe. Has it evolved rapidly enough based on the new climatic condition in Pennsylvania? It's been in North America for almost 13 years. So unlikely, but can't say for sure. It is unlikely that it's occurred in this short time scale. It doesn't mean it can't happen in the future, and a lot more research would need to be done to know if that happens. Now, for it to happen, you do need some form of underlying variation within population. And we did find hatch variability, which again means maybe adaptation one day. Hatch variability in egg masses that were subjected to the same treatment. So maybe that is there for the future. Now, that could be linked to genetic factors, but also there could be a maternal effect. So based on what the mothers or the parents ate, and based on what conditions they were exposed to beforehand. I do want to point out that a study found that parental diet did not impact hatch rate when fed on concubines, tree of heaven, or both. We don't know what the effect of that could be on cold tolerance. Also, there's a study by Bellois and Bem that found multiple paternity for spotted lanternfly. Again, could be a connection to the variability in hatch. So what are the implications? Well, we found that the spotted lanternfly egg masses were more cold tolerant than predicted from South Korea. So that can change the risk assessment models that were made for the spread of the species. And what does that mean for Canada? That's the question. For it to survive winter in Canada, it needs to survive temperatures below 0, actually maybe above -25. And you can see here minimum temperature between 2001 and 2030. There are still quite a lot of areas that don't go below 0 during winter. And there are also a lot of areas that don't have any days in January below -25. Are there risks of incursions? Well, yes, those have happened. There's been incursion in southern Ontario, but also Nova Scotia. Actually, these have come through cruise ships, which is again unpredicted means of transport. So it's really important to stay vigilant because the risk of incursions are high. And if you see any spotted lanternfly, report it to the CFIA. Just to get another idea of what it might mean for Canada, we looked at CFIA observations of spotted lanternfly within Canada. So those are all the red triangle that you can see on the map. That includes Winnipeg, Welland, Ottawa, near Montreal, Quebec, and Moncton, Halifax, Sydney. And we got climate data from these stations to see how many times you would see minimum daily temperature in a winter below minus 27.7. Now, in Winnipeg, actually that happens more than 10 times a year. This data is for the last 50 years, so events when that would happen between winters in 73 up to 2022. So yeah, Winnipeg minus 27. Also, we can see that Winnipeg is the only city here where you see more than 10 consecutive days below minus 15. Then Ottawa and Quebec do have minimum daily temperatures below minus 27. That happens more than once a year, so between 2 and 4 times a year. Near Montreal, so Saint-Hubert is every year you would see minus 27.7, but Moncton, Welland, Halifax all happen every like 2 to every 10 years. And actually Sydney is less than once every 50 years. So overall, the risk to Canada, well, probably quite high in some parts where we've seen incursions. So there has been a study but in the lab from Julie Urban, is from Lee's teacher, and she's looked at cold tolerance for first install nymphs. And I thought it'd be interesting just to see if the first install nymph could make it through spring, in case you thought, oh well, eggs can survive a lot of cold, but maybe they hatch and then they'll still die because we have cold temperatures in the spring. And actually we did find that, just to clarify, minus 2.5 is the temperature at which they die, but they need to be exposed to minus 2.5 for over 15 hours. And minus 7.5 or around thereabouts is the temperature, is the critical thermal minimum. So they would die at that temperature. It's actually a lot higher than was anticipated. In Winnipeg, these temperatures have, this is just the minimum daily temperature, and this happens 7 times a year or twice a year within, well, between April to July. In Welland, it happens a bit less, so minus 2.5 is 3 times a year, well, 3 times a season, and minus 7.5 is every 3 years. In near Montreal, you get from April to June, you see minus 2.5 3 times a year, but minus 7.5 is roughly every 2 years. It's the same 50-year period that I looked at for egg masses. Sydney is a lot lower, 5 times, well, no, you still get 5 times a year or once a year. I haven't done all the cities because this was just out of curiosity. And again, out of curiosity, I had a look what happens if you just start mid-April instead of the 1st of April. And here is actually quite reduced with minus 2.5 happening 4 times a year in Winnipeg, minus 7.5 once a year. And here actually minus 2.5 is once a year, but minus 7.5 in Welland between May and April to June is every 50 years. So yeah, chances of dying then are quite slim. Same for Sydney. This really changes how often minus 7.5 can occur in that period. And same for New Montreal, minus 7.5 would be every 50 years in that time. So there we go. It's it can actually tolerate a lot more cold than we anticipated. And what does that mean for Canada? Well, areas where spotted lanternfly has been observed and where it's potentially warm enough to sustain population are also areas that have agricultural activities. And that includes all the wine regions. So as you can see, Nova Scotia, who thought they may be not as much at risk from spotted lanternfly, well, we can get there. Ontario, Southern Ontario. We haven't really looked at BC because there hasn't been any observations, but I don't think the temperatures there would be cold enough anyway. And same for I messed up in Quebec for Southern Ontario, sorry about that. So it's Quebec here and Southern Ontario here. So just to summarize everything that you've heard, because that's quite a lot, cold tolerance strategy, spotted lanternfly egg masses are chill susceptible. They die before internal ice formation, but it does come close to the supercooling point. There are lower thermal limits, so the hatch rates are significantly impacted on the short term at temperatures at or below minus 20, and for long exposures, so 10 days, 15 days, at or below minus 15. We do suggest that minus 27.7 is a conservative approximation of the temperature at which 100% of the eggs would die. But obviously we did our experiments on 40 individual eggs, so to get a better view of the population, you'd need to test that on more of the species. And that's it for me. Thank you for listening. Before I completely leave you, actually, I just wanted to say, if you're in any of the regions that I have mentioned, so Southern Ontario, even Southern Quebec, Nova Scotia, BC, and you spot the spotted lanternfly, then snap it, catch it, and report it to the CFIA. And there's a QR code here if you need to. So yeah, thank you.
Excellent. Thank you so much, Anna. That was great. We did have a couple of questions come in as you were speaking. So the first question is, has there been any use of North American when looking at the changing distribution models for SLF with this new cold tolerance evidence?
So has it been used yet? No.
Thank you. Another question coming in from Joseph. Are there any data available on microclimate temperatures where SLF is likely to lay its eggs? It's possible that even if air temperature is below the supercooling point, the microclimate experienced by the eggs masses may remain above the SCP.
Yes, no, but we're working on this. So yes, 100% is possible that with the microclimate, they might be fine, especially if egg mass is on the snow cover. We don't actually know what the impact of snow is on the wax covering. So it's possible, but we're planning some field work to be able to measure that in the field. So great question.
Excellent, thank you. The next question is a two-parter, so I'll give you the first part first. So this is coming in from Nelson. My question is, could the SLF delay their hatching until after extreme winter so that their eggs or early larvae remain dormant in probably the soil and continue its metamorphosis during favorable conditions?
It's possible. I don't know. There's work by Melodikina on that. well, not necessarily about the cold, but on the diapause of the eggs. And yeah, it's possible that they could delay their hatch. They don't all hatch at the same time. So they could hatch late April and then still make it there. I did just read the question. I hope that answers the question. Yeah, it's we don't know, but it's possible.
Excellent, thank you.
I did just reread the question from Kim Cuddington. Was that the first question that you read me, Kendra?
No, I haven't gotten to Kim's yet. So if you want to respond to the data access.
So I did have a play with this, but I can't remember what the results were. It has changed, but not as not as much as I thought it would in terms of impact, and at least in terms of which cities experience cold events, if that makes sense.
Excellent, thank you. And then the second part to Nelson's question is it possible for the epigenetics to be altered as a means of phenotypic plasticity, more or less like environment filtering, to increase their chances of surviving winter? He reckons that invasive species have these special abilities as a means of adaptation.
It's possible, but all the slides that I showed on the phenotypic plasticity and adaptation is a lot of speculation on our part, because there's a lot of experiments and further research that would need to be done to really determine what happens there. But it is possible. It has the basis for it, so yes.
It looks like our last question for now, unless any others come through for us, is what are the initial symptoms on trees infested with nymphs or adults?
The initial symptoms for the tree. So there is dieback on some of the branches and the leaves that you can see. Actually, there was, I don't have the picture there, but you can find a lot of information on the Penn State spotted lanternfly. I think it's Stop the Lanternfly or Stop SLF. That has a lot more description on the impact that it can have on the trees. Here you can see actually in the corner from the image from the CFIA that the leaves have started to die back. Also, one of the big tell signs for trees, at least, is the honeydew. Based on what I've heard, there's a lot of honeydew that's being generated by the spotted lanternfly.
Excellent, thank you very much. Looks like that was the last question that has come in for us. Let me just double check here. Yep, it does look like it is the last question. I'm just going to put one final slide up here on my end. There you go. So thank you very much, Anna, for presenting this morning. It was extremely informative, and we value your time and your expertise in this material. I would also like to thank everybody for joining us today. This webinar was recorded and will be shared on the ISC YouTube channel. So take a couple minutes also, if you don't mind, as a reminder to fill out the survey that will be coming out shortly. We would very much appreciate it. And to stay informed of any upcoming webinars in our ISC webinar series, please go to our website, theinvasivespeciescenter.ca, in order to sign up for our email, and you will be able to stay informed and get that information that way. So looking through, doesn't look like we've had any additional questions come in there, just a couple of thank yous and thumbs up for you, Anna. So again, thank you very much. And thank you all for joining us. Enjoy the rest of your day.
Thank you.